Yes, good evening. Unmute. So everything is visible and clearly audible, right, Anil? Okay, I'm just waiting if anyone wants to join. I'm just waiting for at least 5 minutes. From 6:05, I will start our this week assignment problems. Mhm. Okay, I will start from 6:05. If anyone face any problem, please let me know, and then I will start assignment 4. Okay, so it's 6:05 and we can now start. Okay, so myself, Amiya Mandal, I am a PMF scholar of IIT Roorkee. I am working under Professor K.L. Yadav, and this is my week 4 and week assignment 4 of the NPTEL course of Fundamentals and Applications of Dielectric Ceramic, of course code MM31, and the instructor of the courses is Professor Ashish Garg from IIT Kanpur. Okay, so we can start now from question number. Okay, so uh, just I am recapping what you have learned in week 4. Okay, okay, so in week 4, you have learned about the dielectric displacement and polarization mechanism. Okay, and polarization mechanisms for dielectric displacement polarization, and it is just the some extension of this mechanism. And dielectric polarizability 1, dielectric polarizability 2, and the frequency at last, frequency dependence of dielectrics. So in 5 lectures, you learn all about these mechanisms and polarizability and their polarization properties of the dielectric material. Okay, so there are 15 questions in assignment 4 also, and I am just going to solve all the problems. with and discuss all the problems with you uh, in each step of one problem. So, okay. So first, and each problems are based on what you have learned in week 4. Every problems are based on the week 4 lectures. Okay. So first of all, this is a very basic question. Question number 1. The given question number 1 is, as per Gauss's law, you all know about Gauss's law from the, this is a very basic law of electrostatics. Electrostatics, in electrostatics, you all learned about the Gauss's law. This is the fundamental basic law of Gauss's law. Okay, as per Gauss's law, electric flux, you all know about the electric flux denoted by phi. So electric flux is denoted by which term? Which term? Q by epsilon naught, you already know about this. Okay, where Q is the charge, epsilon naught is the permittivity of the free space. Okay, so I am just briefly discussing about what the Gauss's law, what Gauss's law tells about in electrostatic. So in this Gauss's law, the total amount of electric flux, Gauss's law mainly tells about the electric flux. What is the electric flux? Electric flux is the electric field when electric field passes through some surfaces. So this is the surface. You can see this is the surface. When an electric field passes through the surface, through any surface of any material, then in which area it is surpassed. Okay. Then we term the electric flux in terms of the area of the material. Okay. Means in which area the electric flux, electric field is passing through. This is termed as the electric flux. And the concept of electric flux comes from the area, passing area of the electric field. Okay. And flux and electric field and their relation of charges, this everything I told in Gauss's law. So the total electric flux out of a closed surface, this is a very important point. It must be closed. Surface must be closed surface. It should not be open surface. Okay. So when electric flux passes through any surface, the surface should be closed. So the total electric flux passes out from the closed surface equal to the charge of the enclosed, which we have considered the surface. This will be the enclosed surface, closed surface. And the charges closed by the surface is if Q is the closed charge. Okay. Then Gauss's law tell about the flux of the electric field will be the ratio between the charge of the closed surface and the permittivity in the free space divided by the permittivity. This is the permittivity term. You already all know about the Gauss's law and its relation about electric flux and charge, and the question is based on this. Okay, I'm just simply explaining some terms and by figure. Here, this surface is nothing but it is cut from this surface. So this is a sphere and a charge plus Q charge is centered, is situated at point, at a center, plus Q charge. Okay. So if we consider this surface, if we consider the whole surface, so the closed charge is Q. Okay. So the sum of the flux is proportional to the total charge enclosed. Okay. This is sum of the charge is proportional to the total charge, total flux enclosed. Okay. This is the relation in there. So electric flux to an area is defined as the electric field multiplied by the area of the surface projected in the plane perpendicular to the field. Okay, Gauss's law mainly tells about the electric flux and some conditions about the charge restriction, charge charge resides in the closed surface area. Any closed surface is okay. So what is the importance of Gauss's law? It permits about the assessment of the amount of the imposed charge by the mapping of the field on a surface outside the charge distribution. Okay. So these are the Gauss's law and its importance. So Gauss's law and its integral form. What will be the Gauss's law and its integral form? Gauss's law and integral form. This is the integral form. Okay. Where it comes from, came from, what is came from, we have psi equal to q by epsilon naught. What is phi? Phi is nothing but electric field into the surface, delta S. If we take the whole sphere, if we take the whole sphere, want to take, then not we must have to integrate from the whole closed surface. This means about the closed surface, denotes about the closed surface, and this gives this. This is the integral form. Okay, and you can see from this figure also how dA and integration of this and how charges is enclosed. This is the enclosed charge. The area integral of the electric field over any closed surface is equal to the net charge enclosed by the surface divided by the permittivity. Why I have shown here the integral form? Because this integral form is directly related to the phi. This is the electric flux, which I have been asked in the question. Okay. So this is the electric flux. Okay. So this is the integral form of the electric field, and this denotes about the electric flux also. You can see also in this figure where uh, every fields are uh, moving out from this surface area, and if we take this small surface area and we integrate, then we get the whole flux coming out from this surface. And this mainly tells about is mainly are discussed in Gauss's law. Okay, this is there is some clear explanation of Gauss's law. So in integral part, you have seen that integration of E into dA. This is a vector. So this is the vector dot product. This is equal to the integration of total area gives you the total area. Total area curve. Okay. This is the modulus value. Then and the cos theta value comes from the dot product. So flux depends on the theta value. Depends on the theta value. Theta is the angle between area and electric field. Say electric field is directed in this direction and area always directed in the perpendicular to the surface, such that in this surface, this is the rectangular surface. What will be the area? Area will be directed to the perpendicular surface. Okay. So in this case, area will be directed in this range. Okay. So this is the explanation, and this is the source where I have taken these figures and this explanation of Gauss's law and its corresponding electric flux, corresponding integral form. Everything is related to the electric flux, and its dot product also have been shown. So area is also perpendicular to that. It has been also shown. So you can easily find the answer of Q by epsilon naught. Okay. And the Gauss's law. This is when Gauss's law, Q by epsilon naught. But what is the relation of permittivity? Or what is the relation of Gauss's law in, in the study of our dielectric material? In dielectric material, we want to study about to find the capacitance, to find the polarization, and we must have to calculate the permittivity of free space, this question. And it mainly comes from the Gauss's law. Okay. Gauss's law application. So this is important in our start. Okay, question number one, been completed, and I have tried to complete. And the question number two. Okay, I want to just see that everything is going well or not. Just recording is going on. Okay, everything is fine. If anyone faces any problem, please let me know. Okay, I think everything is visible and audible also. Already you have told me. Okay, so we can go forward to the next question, question number two. Question number two is, okay, which of the following is the unit of dipole moment? Unit of dipole moment. Where C represents Coulomb. Coulomb? Okay, where C represents Coulomb. What's the which Coulomb unit? What it represents? What does it represent? It represents charge. Unit of charge. Charge. Okay. It's a Q in SI, of course. In SI unit. Okay. Coulomb is a charge. Measurement of charge. Okay. So to find the unit of dipole moment, we must have to learn about what dipole moment is. Okay. So this is electric dipole. So what electric dipole is? Electric dipole comprises of two charges. One is two equal and opposite charges, plus Q and minus Q. Okay. Plus Q, minus Q. These are two equal and opposite charges. These are point charges. Okay. Point charges that are separated by a distance delta. Delta is the distance of separation between their centers and their centers. Okay. So delta is the separation distance. Two unit positive charges plus Q and minus Q, equal and opposite unit positive charges separated by a distance. Then the resulting dipole moment can be expressed as the multiplication of the charge modulus and their distance. This is termed as the dipole moment. Okay, this is termed as the dipole moment. Okay, this is termed as the dipole moment. Okay, and here's the symmetric figure of dipole moment. So, dipole moment is a vector. What's the direction of the dipole moment? It is directed from negative to positive. It is very important. It is directed from negative to positive charge. Okay, so it is a vector form. It is directed from negative to positive charge, and it has a unit of Coulomb into meter. Okay, from where it came from? This expression. Okay, from this expression. New unit. What will be this? Unit of charge is Coulomb into unit of this separation distance, that is SI unit of separation distance, meter. Okay, Coulomb into meter. Okay. So that's it. And there is a special term of polarization. Polarization is from dipole moment concept. From the concept of dipole moment, we can define the polarization. Polarization is nothing but the total dipole moment, it is the sigma mu divided by V. Means total dipole moment per unit volume present in a material is termed as polarization. Termed as polarization. We will see it later also that what polarization is and what will be its unit. Its unit is Coulomb per meter square. Means charge per unit area. Okay. Means the unit of dipole moment is Coulomb into meter and unit of volume is meter cube in SI unit. So the unit of polarization will be Coulomb into meter to the power minus 2. In the most simplistic way, when all the dipoles are aligned in one direction, P can be written as Nm, number of dipoles per unit volume. You should note that P equal to 0 does not mean that all the material does not necessarily have dipole moments. Rather, it likely that vector summation of the dipole moment is equal to 0. Okay, we must see everything if the new vector direction of all the dipoles cancels each other, then sigma of mu gives you 0, which comes out to be p equal to 0. We will see everything in later. So now we can confine ourselves into the dipole moment unit. Unit of the dipole moment would be what? What would be the unit of the dipole moment? Dipole moment would be kilometer meter. This is the unit of dipole moment. Okay. So we can go forward. The next question number 3. Okay. Just see the question, what you have, it had been told in question number 3 that dielectric susceptibility is expressed as, what is dielectric susceptibility? Expressed as some ratio. Okay, every options are told about the ratio. So you must have to learn about the dielectric susceptibility. This is termed as okay, symbolized as chi. So you must have to learn about the dielectric susceptibility. Okay. So okay, you can now see that. Mm, okay. So in parallel plate capacitor, when it is attached to a uh, external source, okay. In parallel plate capacitor, this is parallel plate capacitor. Okay. Surface charge in vacuum. This is surface charge in vacuum can be expressed as charge per unit area, and charge is nothing but C equal to Q by V. Okay, we know about the capacitance of any parallel plate capacitor. From here, it can be conclude that Q equal to CV per unit area means surface charge density, and CV, C means epsilon naught A by T. A is the area of the surface and T is distance between them. So C equal to epsilon naught E into D, epsilon naught into A by D. So in terms of, if we cancel out A, if you want to cancel out A, then this terms arise, and this is nothing but epsilon naught into E. Okay. Now I'm not just going to explain all this term. Everything had been discussed in your lecture class. I am just remembering all those things what you have learned in the lecture classes, so that you want to able the questions and the answers of the questions. Okay. So in the presence of a dielectric, the net charge density, what will be the net charge density? In the presence of dielectric, this is for free charge density. Where no dielectric are present. This is free. Okay. So in the presence of dielectric, what extra amount will be added? Epsilon r. Okay. So along with surface, some external will be present. So sigma external, this is sigma is. Okay. So sigma external is nothing but the presence of dielectric material. The presence of dielectric material changes the net charge density. Charge density will be increased now with the inclusion of dielectric. With the inclusion of dielectric in the parallel plate capacitor, the net charge density is increased by the amount of sigma external from the inclusion of epsilon r. Okay. So net charge has been increased, and it can be expressed as vacuum plus sigma pole. This is termed as the polarization term. Okay, this is termed as sigma pole, polarization. Okay, sigma charge density of polarization. And this is also called rho. Rho is the extra charge resulting from the polarization of the dielectric. It's very important. This comes from the polarization term. Polarization of dielectric. If you already are aware of polarization in the dielectric material after the application of the electric field. So this came from the polarization of dielectric material. And this term always makes difference in the electric field. So we try to understand what is the displacement electric field. This term D is called the displacement electric field. And it is nothing but charge per unit area. Okay. It can also be expressed at this in a when dielectric materials are present. When dielectric material is present. Okay. So we can say this. And D will just like epsilon naught plus T. This term makes difference when we calculate the T value. So from this above expression, we can see that epsilon naught into E into V, and we just put this value. So we can compare this T equal to epsilon naught T into E plus epsilon naught T plus T. Okay. So what T arises from? T is nothing but epsilon naught into epsilon minus R. And this epsilon minus R equal to epsilon minus 1. This is termed as the susceptibility. Okay, susceptibility. This is the susceptibility. So we can see that susceptibility depends on epsilon R value, depends on the relative permittivity of the dielectric material which we have inserted in the free space of a parallel plate capacitor. So when it goes increases, susceptibility goes increases. So it determines the property of the dielectric material in the application of the external electric field. How does it respond? How a dielectric material would respond will be determined from this property, this constant susceptibility. So the response of response, okay, response of dielectric material, dielectric in external electric field, external electric field. Okay. So this is term in case, and so these terms occurs, and if from this equation we can write this polarization. This is occurred. Polarization is occurred due to the bound charges inside the dielectric material, and this is the external surface charge. This occurs from the external surface charge. So this is nothing but the ratio of this. This comes out from the bound charge and the surface charge. Okay. This is the surface charge and bound charge ratio. Or in other term, this is the ratio between the polarization and external electric field. Okay. Okay, I have highlighted this portion as nothing but the ratio of polarized charge or the excess charge to the surface charge in the vacuum capacitor. So what we have inserted the excess charge after the implication of the dielectric material inside the parallel plate capacitor. The ratio of this excess charge and between the ratio of the excess charge and the surface charge gives the value of susceptibility, which is a measure of how dielectric material responds in an external electric field. This is a very important parameter to understand. Okay. So the region of polarization, okay, you can read it from this. I'm just telling that the total charge density, it had total charge density now is free charge density, that is the surface charge density, and the bound charge density arises from inserting the dielectric material. Okay, I just been inserting the dielectric material. And this bound charge is nothing but the Del dot P. Del is divergence value of the polarization. Polarization is nothing but the dipole moments per unit volume. So, if we diverge all the in physical term, if you want to diverge all the dipole moments, we get the bound charges inside the material after the application of the external electric field. So this all gives this, and from this we have already run, I have already shown everything. So from this concept, based on this concept, we can now tell that dielectric susceptibility is expressed as option number A, ratio of bound charges to the free charges, and ratio of exchange B is not correct, free charge, ground charge, and the proportionality constant between induced polarization and applied electric field. Okay, these two options will be correct. Those option A and option C. Okay. Okay, now we can go forward to the next question. That is question number 4. Okay. So question number 4 is telling about the what is the net dipole moment per unit volume signifies as in a dielectric material. In question number 2, when I was doing the unit, the calculating the unit of dipole moment, I already have told what the net dipole moment per unit volume signifies is what the term P is denoted, how the term P is denoted. That is polarization. That will be the polarization term. Okay, it will be polarization. I think that's the polarization. Net dipole moment delta mu by V gives you the polarization value. Okay, gives you the polarization. Net dipole moment. This is the net dipole moment. Net dipole moment delta mu sigma mu inside the material. Per unit volume, it gives you the polarization value. Okay, I am just recapping all those things again in this. So this is the net dipole moment. I already have discussed about it. This is the polarization value, net dipole moment per unit volume. And I already have told the um, unit of the polarization. The polarization is Coulomb per meter square. Okay, charge per unit area. Okay, so this only the polarization. Now move to the question number 5. Question number 5 is telling about with the increase in temperature, ionic polarizability. How it is temperature dependent. Ionic polarizability, how it is temperature dependent. Increases as T or decreases as T or remains independent of temperature or increases as T to the power half. So how ionic polarizability depends, you will see that. So to see the dependency of ionic polarization in temperature with temperature, we must have to learn about the ionic polarizability. So what ionic polarizability is, you can see this explanation that what ionic polarizability is. I will later discuss about different types of polarization, including electronic polarization, ionic polarization, dipolar polarization, interfacial polarization, and their dependency of with frequency. Okay, so let's try to understand what ionic polarization and ionic polarizability. Polarizability and polarization are different things. Polarizability is net dipole moment per unit volume, uh, per unit electric field. Okay, that is called polarizability when electric field is considered. But net dipole moment per unit volume gives you the polarization value. Okay, so what ionic polarization is? Here we have considered ionic material. Ionic material gives the ionic polarization. This is simple. So, such that NaCl, plus and Cl minus. This is Cl minus the higher radius atomic. We always know in ionic material, radius of anion must be greater than radius of cation. Okay, you already learned about the previous lectures and previous assignments. I also have told them in details. Okay, so what does happen? What does happen when external electric field is applied in this ionic material? In this ionic material, when no electric field is applied, then what is the value of mu? This is the center separation. This gives mu. This is the center separation. This gives mu. And both are directed in opposite. So what will be the net dipole moment? Net dipole moment gives you the zero value. But when we apply some electric field, external electric field on the material, how the material respond? Material respond with the electric field and it displaces from their position. You can see that this red color signifies and the point signifies their original position. And you can see that every spheres have been separated and has every spheres of cation and anion spheres have been separated from their position. Okay, polarization means separation of displacement or separation of the charge material. So these ionic materials have been separated from its original position. Have been separated from its original position. That gives the, but in these cases we cannot find the dipole moment as zero. Okay, here we can find the net dipole moment because the magnitude of the dipole cannot cancel each other. Do not cancel each other. There must be a net dipole moment. This net dipole moment depends on what? Depends on electric field. And polarizability is determined as net dipole moment per unit volume, per unit electric field. It is polarizability. Okay. So here is the calculation of how ionic polarization can be calculated and how it is dependent with temperature or not. Okay, everything we will see. So the distance between ions has termed as d value uh, and increases by d with opposite direction. So the calculation of quantity. So the force, their force will be there between charges. If we apply electric field, the force will be this. And there is a restoring force when positive anion and negative cation, they are connected via spring. Okay, always they connect via spring always. So what will happen here? There must be what? Restoring force. There must be restoring force. And this restoring force and this force will equal equilibrium to each other. Will be equilibrium to each other. And after this calculation, I am not going to just doing every calculation. I am just understanding the fact where the polarizability is dependent or not. So from here, D has been calculated. And from you can see this relation, the relation of mu, that is the net dipole moment. Net dipole moment, there must be net dipole moment. Okay. So net dipole moment depends on q square, E, Y, and D. D is fixed, E is fixed. So, and Q is also fixed. Fixed means, so it actually alpha is the polarizability of ionic polarizability, alpha I. It actually proportional to the Y value. Y is Young modulus. Young modulus. Young modulus. So no dependency of temperature here. You can find no dependency of temperature. Okay. Only it depends on the strength value. Y value is the Young modulus value. When an ionic compound, the strength of the ionic compound is greater. Strength of the ionic compound is greater. What will happen? Strength means its capability of polarization will be decreases. It will be oppositely related, inversely related. Okay. So this has been told here. Y term denotes the strength. Okay. So based on this concept, we can easily say that it remains independent of the temperature. It do not depend on temperature. Do not depend on temperature. It is independent of temperature. So ionic polarizability is not dependable on function of temperature. Okay, it's not dependable on function of temperature. Okay, so we can go forward to the next question. That is question number 6. Okay, what question number 6 is telling about? We just want to find out what question number 10 is going to tell. Just 1 second. Just okay. So the ionic polarizability contribution to the dielectric constant at a frequency of 10 to the power 15 Hz will be what? So we must have to learn the dependency of ionic polarization with the variation of frequency of the to the dielectric constant. We must have to learn that. After that, we can um, answer this question. Okay. So there are 4 types of polarization: electronic, ionic, dipolar, and interfacial polarization. Electronic polarization. I am just explaining um, very briefly what electronic polarization tells about. In an atom, in an atom consists of a nucleus and its corresponding electron clouds. Electron clouds. Okay. Nucleus and electron clouds. When we apply the electric field, electron clouds gets separated from its position and gets accumulated, not gets separated from this position and gets looks like. And there should be a net negative amount of charge, yes, or this side, sorry, this side. It will react in this side. So this will be the net opposite charge. That's okay. So, and the net charge, this is the net charge. Net positive charge, net negative charge. Okay. So what will happen? These two net negative charge shifting of electrons is happening here, and this is called the electronic polarization. Second, what is the ionic polarization? Ionic polarization is happening between the ionic solids, means in cations, in between cation and anion. When no electric field is applied, their positions are intact with their positions. When external field is applied, we apply external electric field. What will happen? There is a shifting of their of cation and anions from their original position, and it gives some polarization value. And of course, when polarization is we get polarization, there must be dielectric constant, and this dielectric constant value dependency. Okay. And what is the dipolar polarization? Dipolar orientational polarization. It is nothing but when no electric field is applied, the dipoles are oriented in this direction. This is a negative to positive reaction. Two negative charges and two positive charges are there, and their net dipole moment is oriented there. No electric charge field applied, their dipole moment is fixed. But when we apply electric field, these positive charges will shift to this direction. This negative charge, positive charge will shift. So when we apply electric field, the charges try to align themselves on their field. Okay. So net dipole moment will also be changed in this direction. So this change occurs in dipole cases. So we tell that dipolar polarization has been created here. Next is interfacial polarization. When interface is created or any voids or any defects are present inside the crystals, then these types of polarization arises. So interfacial polarization, this is the dielectric material and this is the electrode. Okay, this is the electrode. Electrodes have been inserted here. So the uh, interface between electrode and the dielectric material gives the interfacial polarization. And this is the voids, some voids present. This is the voids or some impurities may be present, impurities. So everything, these voids, impurities are inside, sometimes grain boundaries. Okay, grain boundaries. Everything gives the interfacial polarization. Everything gives the interfacial polarization. So, so these are the interfacial polarization, dipolar orientational polarization. You have already learned it. I have just reminded you. And this, first of all, atomic polarization or what polarization? Electronic polarization lies in this range, 10 to the power 13 to 15 hertz. And ionic polarization lies in this range, 10 to the power 9 to 10 to the power 13. And dipolar polarization happens in 10 to the power minus. And at the range of 10, only 10 hertz, interfacial space charge polarization happens. You have to remind this range. Okay. And in non-magnetic dielectrics, Maxwell electromagnetic theory predicts that at the very high frequency means at the electronic contribution, when electronic contribution, we consider only the electronic contribution, then we can tell that epsilon r dielectric material has the property its epsilon r equal to n square. N is the refractive index of the material. It's simply equal to the square of the refractive index. So this is the equation. This is these three terms are put on the electrode material would be there. There is the variation. This is the very important term. Variation of dielectric constant with frequency, and it gives at a very large frequency 10 to the power 16. And this region is called the resonance polarization region. Okay, this is also the resonance polarization. This is the relaxation region. This is the relaxation region. This is the relaxation region where dipolar relaxation we will see in the next lecture. Interfacial space charge relaxation, but in these cases, ionic and electronic cases, no relaxation would be there. Okay, so there is ionic level, there is a sudden resonance should be there at this region of 10 to the power 15 and 10 to the power 13 region. Okay. So how it is varying, this is delayed at very small frequency range, 10 hertz, we always see the interfacial polarization. And when we increase the frequency, we see the decrease of interfacial polarization. No interfacial polarization should be there. Again, if we increase, only the ionic polarization consists in there. And again, we increase the electronic polarization. So electronic polarization are present in every material. And why it is decreasing and why actually F is based on the time. How a material, how fast or how slow a material is responding with the electric field. If a material respond very fast means T is very uh, T is very less, Okay. If T is very less, then frequency will be very greater. So when every material shows electronic polarization, it also depends on proportional to mass. Okay, so okay, I am not going to get in details of all this. Just so what will happen at a frequency of 10 to the power 15 hertz? Will there be any ionic polarization? No. At the region of 10 to the power 15 hertz, there will be only the uh, electronic polarization. Electronic polarization exists in 10 to the power 15 hertz. No ionic polarization will be there. So only this option will be correct. Okay. Okay. Now we are going to question number 7. There is a problem given that in a water drop of 0.1 centimeter radius, water drop of 0.1 centimeter means 1 mm radius, 1 mm radius. So what will be the volume of this material? 4/3 part 10 to the power minus 3 meter cube. Okay, this is the volume of this material. All the molecular dipoles are pointed in the same direction. So the net dipole will be same. Net dipole, there should not be think about the net dipole. Okay. If the dipole moment of the water molecule is, so net, there will be a net dipole. Dipole moment of the water molecule is also given. 6 into 10 to the power minus 30 coulomb into meter. This is given. You have to just find the polarization. Polarization is sigma mu divided by V. But there is a concept. Sigma mu is given for what? Which case? Of a water mole. Sigma mu is given for only a water molecule. Is given for only a water molecule. But the question is the water drop. For water drop, how many water molecules will be there in a water drop? So you have to calculate the volume of this water molecule, and for the volume of a water molecule and the volume of a water drop, and we have to multiply just how many water molecules in a water drop are. Okay, I have just calculated. Uh, um, in these cases, you have to consider the molecular mass. Molecular mass of oxygen. Uh, Water is how? This is 2 plus 2 and this is 16, gives you 18 value. So molecular mass of water is 18 gram. You already know about this. 18 gram contains this molecule, and for only one molecule it is given. Only one molecule it is given. Okay, only one molecule, only one water molecule, the dipole moment is given. We have to find for a water drop. Okay, so that is, so 18 gram divided by 10 to the power 13 meter molecule of water contains what type of molecule? This type of, just multiply 10 to the power 23 into 10 to the power 3. So this molecule will consist there. And volume of the water drop we have calculated. So number of molecules in a drop. What will be this? Just multiply these two, 10 to the power 16. Just find this value, and polarization value will be just multiply this value and this value. This value. Okay, just multiply these two values. Two values. One is calculated from this and other is given. You can easily find the answer is this. 8.4. Okay, 8.4. This is the concept. You have to consider the whole water drop, so that you have to multiply how many water drops are present, how water molecules are present inside the drop. Okay. So these are the questions of up to I have just I am just checking whether everything are fine or not. Okay, just wait only 1 minute. Okay, recording is going on. Okay, everything is fine. Okay, now we are going to the next question, question number 8. Response setting. Question number 8. Okay, just 1 second. Just read the question. What the question wants to tell that. Okay, the question is, what is the correct order? What is the correct order for the various polarization mechanism in terms of their response with increasing order of frequency? Increasing order of frequency. So various polarization mechanism I have um, told you. Various polarization mechanism I have told you. Okay. And what will be the this range in this range? So I have just so I have told about the various polarization mechanism. I have found this. So this is electronic polarization, and in this region does this apply? In this region, electronic polarization is applied. Okay, and this is the increase of frequency from 10 hertz to 20 to 16 hertz. And how the frequency is changing from audio frequency, radio frequency to visible frequency. Okay, so in this region, in this plateau, this is called plateau. In this region, electronic polarization. This is four polarization have been told here. Mm, two, three, four different types of polarization have been classified here at their different electric field. When no electric field is applied, when electric field is applied in this direction. Okay, so negative and positive charge separation has been shown here. Negative and the atomic position changing gives you the ionic polarization and the dipolar polarization. And this is the space charge polarization at each grain boundary. Okay, have been shown here. So you can see that uh, at a very high frequency, only electronic polarization and at very at near about 10 to the power 30 is ionic polarization stability is varied in this region. Okay. And the dipolar polarizability and the space of polarizability is here. Okay. So what will be the order? Order will be correct order will be first electronic polarization must be greater, then ionic, then dipolar, then interfacing. Okay. This is the correct order of polarization inside the material. Okay. Next question. Anything? Any problem? Okay. So we can go forward to the next question. Question number 9. Okay. Question number 9. Just see what question number 9 is telling about. It is telling about the potential energy of a charged dipole is minimized when the potential energy of a charged dipole is minimized. Potential energy of a charged dipole, you already heard about the dipole, electrical charge dipole. Okay. Separation of positive and separation of negative charges. Plus q minus q are separated by a distance d, and this gives mu equal to q into d. Okay. And what will be the potential energy? Potential energy is nothing but when external electric field are applied. External electric field is applied. Okay. So this gives you the charge potential energy of a material. So how potential energy is dependent? How potential energy is dependent? How potential energy is minimized, not dependent, is minimized on when dipole or electric field are collinear. Means you have to understand how dipole and electric field are arranged. Dipoles and electric fields are perpendicular. They are at 45 degree or 60 degree. Which option will be correct? To find the answer, you have to learn about the torque on electric dipole. About the torque on electric dipole. Okay, the torque produced on an electric dipole, you can see this dipole. Okay, you can see this dipole as this is the dipole. This is the dipole. Okay, and in this direction, electric field is created. And what is the direction of this dipole? It is from negative to positive direction. Dipole will be from negative to positive direction. Dipole is termed here is P in terms of P. Okay. It can be termed as P, can be termed as mu. Everything small p. And what capital P for? This is polarization. And this is dipole moment. Okay. Two things are different, capital P and small p. So you can see that the displacement of the dipole, when it is um, the dipole is placed in an external electric field. External electric field is applied dipole. It is moved from its original position. And what will be the direction of this position? And if the direction is given by the left thumb rule, this is the left thumb rule. You can see um, that torque will be there in this left thumb. This is the left thumb. The direction of torque will be in this region. Direction of torque is nothing but speed. Okay. So E is directed in this direction, and just hold it out the hand. So give in this direction, and it will get the torque value. Here is also even. Okay. So this is the torque value, P cross E. So this is negative. Okay. Now this is the torque. This gives you the torque value. But what will be the energy value? Two things are different. One dot product, one is dot product, one is scalar product. Means scalar, or this is scalar. It gives the vector product between mu and electric field. So when we place a dipole and external electric field. The force, this will be a force in this direction, this will be force. This will align with the direction of the, this force tries to align the dipole with electric field. So this is the torque we have seen. Okay. From this torque expression, we can also find the energy. From this torque expression, we can find. So an electric field produces a torque on a dipole. This is torque produced by electric field, which where P is the dipole moment and E is the external electric field, which tends to take to its low energy configuration. So energy should be very low in which configuration where the stability is very, where the material, the dipole will be very stable, in which region where the energy is very low. Okay. So where the energy should be very low. First of all, you have to calculate the energy. And it is varying theta, this is theta, from 0 to theta degree, 1 minus cos theta. So when energy will be minimum equal to 0, equal to 0 at 90 degree, theta equal to 90 degree. Energy should be minimum. So this theta will be 90 degree, energy should be minimum. Means at this position. When this to this. Low energy configuration, positive side should be there, negative side should be there, and their direction means it should be stable. High energy configuration, two forces are applied in this direction, which will be unstable. Okay, so E dot E would be the expression of energy. That's a scalar product. So, what is the question? Potential energy of a charged dipole is minimized. When the potential energy of a charged dipole is minimized, it is minimized when dipoles are collinear, means theta equal to 0 degree or 180 degree. Minimum for mu into minimum value or plus minimum value. When what's solving? That is the stable. So that is P into P or into P should be there in the stable configuration. Okay. So when it will be minimum, what will be the correct answer? Dipoles and the electric fields are collinear when, then it will be minimum. So option number A would be correct option. And option number B, telling about dipole and electric field are perpendicular. No, when they get perpendicular, there is no value of no, is a very high value of imbalance. So dipoles and electric field are 45 degree. No, only the option will be when they will collinear, means 0 degree or 100 degree. Okay, we are going to the next question, question number 10. Okay, but just see the question number 10, what it is just going to tell about that as the temperature increases, the dipolar polarizability. We already have learned about the uh, um, electronic polarizability, ionic polarizability. Okay, polarizability is nothing but sigma mu divided by E. Okay, so we have seen that for ionic polarizability, it is proportional to RQ. It is proportional to 1 by Y. And the question is asked about that what is the dependency of dipolar polarizability? Dipolar polarizability alpha D is proportional to which? You will see that it is proportional to 1 by T. So the answer will be decreases as t. Okay, I'm briefly explaining what a dipolar orientation polarization is, and so that you can understand the dependency of dipolar orientation and polarization and its polarizability with temperature. Here, the famous Maxwell's equations have been incorporated, Maxwell-Boltzmann theory, um, and from that, theoretically, it had been calculated that how orientational polarization is dependent on temperature. Okay, so in the case of dipolar polarization, we have materials where the dipoles are present independent of each other. Where the dipoles are present independent of each other and they don't interact with, they can be rotated freely by an operated field, like in case of ionic polarizability. Okay, so with one such example like H2 molecule, it shows dipolar polarizability, which has a dipole moment, and these dipoles moments are free to rotate and can have orientation with respect to neighboring molecules. You can see this is the figure. Each water molecule are randomly distributed. Randomly distributed. Okay. Each water molecule are randomly distributed here. Okay. So in case of random distribution, in every direction centered in a point, every direction dipole moments will act. Okay. So net dipole moment will be zero in case of random distribution. Now, when we apply the electric field, what will happen? We will see. It is quite obvious to figure that the absence of an electric field. Here, no electric field are applied. Sorry, no electric field are applied. So, electric field is randomly distributed and net dipole moment is zero. Okay. When we apply an external electric field, what will happen? So we'll see. We'll see. So parallel to the prepare x-axis, the section dipoles field lower their electrostatic energy and minimum the dipolar energy. We have seen in the energy related problem in the previous problem, every dipoles want to stay in its minimum energy level. Okay, so it will align along the electric field at the minimum energy electric field. So dipoles would tend to align to the applied to lower their electrostatic energy and lead to the minimum dipole energy. Okay, this is the very important line. When we apply the electric field, how the dipole will arrange? The dipole winds will arrange themselves along the electric field, where the electric fields are directed, so that their electrostatic energy are minimum and lead to the minimum dipolar energy. That is the But for instance, water does have a pretty large dielectric constant of 80, which means that there is a obviously some orientation along the field. Okay, so 80 dielectric constant is very high. Okay, this is if the refractive index we see of water, it is nearly about 4. So if we so only the electronic contribution, it is follow 16 value plus there should be some value of ionic polarization. Okay, ionic, and the left will be for dielectric polarization. Left will be for dielectric polarization, dipolar polarization. Okay, so with field, you can see the effect of electric field on the dipolar orientation. Okay, this was the first case. Okay. And without field have been shown in black arrow, and with field have been shown in the red arrow. You can see in each and every cases, there is a displacement. In these cases, we cannot say that the net dipole moment is zero. We cannot say this. we cannot say this that net dipole moment is 0. Okay, there must be a dipole moment. Okay, so you can see that this is the two-dimensional schematic diagram of a charged dipole aligned with respect to the applied field. Okay, this is the two-dimensional, right? In this, there is an electric field we are applying, and delta is the angle between the dipole moment and the electric field, where if we want to try to calculate the energy, mu into cos delta, okay, as it is talked about. So here we have to engage in the thermodynamical concept, where we will minimize the free energy delta G, and delta G also depends on the H and minus 2 interface. H is the internal energy, S is the entropy. So if we increase the entropy, then this term and delta G also this term increases, delta G minimizes. So either we have to increase S, either we have to decrease H, internal energy. These are the very important, and so that delta G decreases. Okay, so that delta G decreases to get the stability or to get the lower minimum energy state. Okay, this is the concept we have to apply here. So here internal energy U of a dipole. We have already learned about this, that when, when we need in minimum, when dipole is completely aligned with the field, and maximum when theta is 180 degree. Okay, theta is 180 degree. Energy of a dipole moment will be expressed in these cases. So in three-dimensional measurement, it is depending on theta value. Okay, dipole cone. This is called the dipole cone. Dipole cone is made, and this depends with the value of delta value. How in three dimension, how it will move around? It will move around, creating a cone with a direction of the electric field. So with a direction of the electric field, creating a cone, every dipole moments will be arranged. And we need to calculate the number of dipoles at an angle theta, that is in theta. Okay, I have to calculate the number of dipoles in theta. And we have to apply the Boltzmann statistics to calculate the dipole moments and the number of dipoles in this region. This is conical region. This conical region, how many dipoles are arranged. So this is the formula depending on the Boltzmann constant. It is U theta depending on theta. Energy must also depend on theta. And the number of dipoles, this is the formula from Boltzmann equation. This tells us about the number of dipoles in a cone. But if we consider whole sphere, and this cone is displaced with d omega, that is called, this is cone at first position, and it is displaced with d omega angle. This is called the dipolar cone. This is also called solid angle. We have also learned in mathematical physics in solid angle. We just apply the solid angle concept here, that in solid angle, okay, it contains dr, r d theta, r sin theta d phi. So component r, sorry, r sin theta d theta d phi dr. Okay. So this is the volume element, and so that we have to just want to calculate. So in this region, and this is the, I'm not just going to go to the details of the calculation. From here, we can calculate the net dipole moment. Net dipole moment. in a dipolar um, to calculate the dipolar polarizability. Net dipole moment we can calculate from here. So the total dipole moment is nothing but the sum of the components of the dipole moments in the direction of the applied field. So it is just the multiplication of md omega and mu cos theta. Okay. So the average, what will be the average? We have to just average it to calculate the adding adjustment. So we have to just integrate everything. Okay, from 0 to pi. 0 to pi. Solid angle. Solid angle will be 2 pi cos theta sin theta. And after putting all the value and the calculating, okay, and we here consider beta equal to mu by kbt and x equal to cos theta. That are the equation. Okay, so what this term coming out from. So this total term is termed as L of beta. This is Lange-Bach function. Lange-Bach function. Okay, Lange-Bach function. So it depends on Lange-Bach function. Beta is nothing but kbt. Okay, beta is nothing but mu into kbt. Okay. So Lange-Bach function depends on theta and beta, and variation of Lange-Bach function and the asymptotic plot. One value and zero value. What one value and zero value gives? This is zero. And when L beta is 1, for large value of beta, means it's proportional to 1 by t. Means t is very small. When t is very small, beta is very large. Means at very low temperature like 30K. Okay. So it is going to just saturate. And when beta is very small, then temperature is very high, higher temperature. Then slope is 1 by 3. This slope is 1 by 3. Okay. Just multiply the slope into beta. You will get the Lange value and put the value inside it. So this is the final expression when beta higher temperature, and from here you can see this expression of alpha. This is alpha expression. Okay, alpha D means dipolar polarizability. This is called dipolar polarizability. It depends on temperature. From here, from this concept, we can say that dipolar polarizability increases as temperature decreases or decreases as temperature increases. Means it depends with temperature inversely. Okay, when are very high and temperature is very low. Temperature dependence of gas calculated, right? So this is the case I have already discussed thing, and based on this concept, you can answer that how dielectric dipolar polarizability depends on temperature, so it decreases as T. It decreases as T. This will be the final answer. Okay. Question number 11. What is question number 11 telling about? Which of the following materials may exist in polar forms? In polar form. Here, four types of materials have been given. First of all, methane, CH4, then carbon dioxide, then water, then polyvinylidene difluoride, PVDF. Polyvinylidene difluoride. No? Two fluoride ions will be there. Okay. And polyvinylidene, it has a complex structure. So to find that how um, the polar form will be there, means how it will respond in the outside electric field. So we must have to see their polar structure, the internal structure of this material, so that we may want to we just find out that how they will respond. So first of all, methane, how methane will respond and what is the structure of methane. Okay, just see. So methane has a central carbon atom, and so this is a tetragonal like structure. You can see that at each is forming crystal, and at the center carbon is situated. Okay, so carbon at the center atom is covalently bonded with hydrogen, and at each hydrogen atom is bonded with hydrogen atom. This is the structure of hydrogen. Now, how dipole moment will act? This will gives delta positive, so this will gives delta negative, and the direction, and every direction will be from there, and red direction you can see here also there. So how they are balanced? Okay. The shape of the methane is tetrahedral shape with a bond angle of this. Electronegativity of carbon is 2.55 and that of the hydrogen is 2.18. Okay, so what is electronegativity? Electronegativity, tendency to attract electron toward any atom. Okay, so carbon electronegativity of carbon is much greater than sometimes greater than something greater than hydrogen. So it has the tendency to polarize the electron. So in these cases, so carbon is most electronegative than hydrogen. It pulls the shared electron pairs toward itself. Therefore, it acquires a partial positive charges and the hydrogen acquires a partial negative charges. Okay, partial negative charges. And the difference in charge distribution makes CH bond. However, the methane has symmetrical shape. Okay. So each CH has dipole moment. The symmetry cancels all the dipole moments. Here, all the dipole moments will be cancel out. All the dipole moments will be cancel out. So delta mu will be 0. This is a symmetrical material. Okay, so dipole moments, all the dipole moments will be cancelled out. Okay, 0. So net dipole moment in these cases will be 0, making it non-polar. So CH4 methane is a non-polar molecule. Okay, you can see from its structure. And what is about the carbon dioxide? What is the polarity of carbon dioxide? Carbon dioxide is made out of two atoms of oxygen. You can see that how and carbon, how the dipole moment is creating. There is a dipole D1, delta 1, delta negative, delta positive, and this is the double bond. Okay, so double bond, um, double covalent bond. Okay. And angle between this is 180 degree. Now, what is the reason? The oxygen is more electronegative. So, electrons are pulled here, and delta negative would be there, delta negative would be there, and two delta positive would be there. So, two delta positive are balancing delta negative and delta. So, this is also symmetric. Okay, this is also, so they will cancel out and leaving net zero dipole moment. Here is also dipole moment. Net dipole moment will be 0. Net dipole moment will be 0 here. Okay. So this is non-polar. Carbon dioxide will also be non-polar. Okay, let's see for hydrogen atom. Sorry, water. For water, we can see that they are creating 104.5-degree angle with oxygen molecule. Hydrogen is and oxygen has higher electronegativity than hydrogen. Then it is so their two delta negative is greater than delta positive and delta positive. So there must be a delta mu. Okay, delta mu value would be there. Hence, a net dipole moment would be there. So net dipole moment will be in this direction. Okay. Okay. So one is directed in direction, one is directed in direction. So net dipole moment will be in direction. Okay. Water molecules attract each other, form hydrogen bonding. Moreover, water confining to container exhibits surface tension. Water attracts other polarity like sugar, amino acid, and it dissolves. Okay, these are some properties. So, water polarity is important. So, water is a polar molecule. This is a polar molecule. Polar molecule. Okay. Here you can also see that how oxygen has a electrons 1s2, 2s2, 2p4. Okay. So, uh, they are stable and four electrons are currents like this, and these four electrons to px, py, pz makes contribution. Okay, right, two. Here hydrogen has one, so hydrogen molecule and one oxygen molecule bonds hydrogen and one. This is hydrogen bond. Electrons are pulled towards oxygen due to electronegativity. That is difficult. Okay, next we are just seeing the figure of PVDF. Uh, Again, this is the PVDF, polyvinylidene difluoride. Okay, this is the figure. You can see some net dipole moments will be there. Net dipole moments will be there. In this case, all transition event. So we can say that this is also the polar molecule. This is also the polar molecule. We can confirm it from the figure. Okay. So what will be the answer that which materials do exist polarity? One is water, one is PVDF also. Okay, these two answer would be correct. Okay, now we can move forward to the question number 12. For a perfect dielectric, what is the relation between charging current and voltage? Relation between charging current and voltage. Okay. Okay. How current is lagging behind, how current is leading, or which behavior current will show. Okay. So for an ideal dielectric, okay. So sinusoidal wave, we also know if we apply a sinusoidal field, it's like this. Means charging and discharging will be same. Okay, will be same for an ideal dielectric cases. Okay. If we apply this sinusoidal field, then how current will be changes? Current is nothing but the rate of change of charge with time. And for a dielectric material, Q equal to CV, C is fixed, the voltage will be changed. Okay. So voltage change gives you what? This D from there, dV dt, just V naught is constant, omega t will be out there. Okay. And exponential of I omega t should be there. So just omega t into CV. C is constant, and this value again tells about the V. So I omega C, this is, and what now from this expression, just multiply with the power of exponential of I pi by 2, which is nothing but and pi by 2 plus I cos pi by 2, that gives you 0, that gives you the value 1. So just multiplication of this, nothing changes this relation. Okay. And this gives this exponential I omega t plus exponential, just they will add up each other. And this value, this omega t plus pi by t value has a significance. What does it signify? The pi by 2 value, this pi by 2 value implies that the current leading with voltage, because in case of voltage only that will be there, and in case of this is omega t plus pi by 2, so it is leading by 90 degree in a perfect dielectric. Okay, so here you can see the graph between the phasor diagram. This is called the phasor diagram. Phasor means phase between voltage and current. Okay, when we are increasing omega, you can see this is 90 degree. Okay, so that is the dependency of current voltage with angle. So what we can see, we have seen that current leads the voltage by 90 degree. This will be the correct answer of this question number 2. So what will be the question number 13? So, which of the following ionic compounds is likely to exhibit highest polarizability? Highest polarizability. Ionic polarizability. Ionic polarizability, we have seen that it depends on 1 by Y. Okay. Y is the strength. Young modulus. Young modulus. Okay. Strength is also Young modulus. So it depends on Y. We will see how alpha I is depending on Y. We have previously seen also. Depending on the value of alpha I, we can also see the zinc oxide, sulfide, selenium or telluride, which will show the highest polarizability, highest ionic polarizability, which will show highest ionic polarization, which has the lowest strength, and it depends on the how selenium, or how the atomic structure of selenium, how the tellurium atomic structure of oxygen or tellurium, it depends on this property, and from this you can say. So we have already learned about how ionic polarizability is generated from the displacement of the ionic charges, means cation and anion. In these cases, delta mu equal to 0, but in these cases, net delta mu is not equal to 0. This signifies the main parameters, where we already have learned all about this. Okay, B value, and this is the final dipole moment arrangement of the uh, ionic polarizability, where ionic polarizability is termed as Q square by I into D naught. Okay, so the above expression tells us about the stronger bond leads to a smaller polarization, which seems obvious because you would not be able to stretch the atoms too far. This is very important line. Stronger material shows smaller polarization. So ionic polarization will be small for stronger material. Okay. So here, when ionic polarization increases, dielectric constant will also be increases. So they are proportional. Here we have some list has been given of dielectric constant, we can see that dielectric constant of oxygen, zirconium in these cases, zirconium, oxygen, sulfur, selenium, dielectric constant is increases because of the decrease of the increases due to increment of decrement of y means decrement of strength. Okay. Strength is decreased this element due to the large ionic sphere. Okay, you can see. So this is called the stiffness factor, stiffness of the bond strength factor. Okay, ionic polarizability. And it also tells the low ionic polarizability for strong bond. Okay, you can see the periodic table which tells us about the table of polarizability. Here, all the polarizability value of each material have been tabulated here. You can see that for each table, which is showing oxygen, which is showing this is oxygen value. What is oxygen value here? What is sulfur value for sulfur? Oxygen, then sulfur, then selenium, then tellurium. In every cases, you can see that it is increasing. So in option zinc oxide, equital, zinc sulfide, zinc selenium, zinc tellurium. Okay, it depends on this material. It has the so it 8, 16, okay, then 34, then 52. Means the atomic number is also increasing. Atomic number is also increasing. That's why the um, electrons in the orbit is also increasing at the valence shell, and the valence shell electron increment gives the tendency to lower strength. If it gets lower strength, it has higher tendency of polarization, and higher tendency of polarization gives higher ionic polarizability. Higher ionic polarizability will give higher dielectric constant. So, based on this, we can also see that for this is also a table uh, from a famous research paper, Physics Review letter from 1968. You can also see that they have also um, experimented with different types of material and calculated their epsilon naught value, dielectric value. You can see that the dielectric value for this zinc oxide and sulfide selenium, this periodic column value have also been generated, and you can see that for tellurium value, it is also highest value for this tellurium value. Okay, so based on this concept and information, we can now answer the question number 13. What is tellurium? So the answer will be exhibit highest polarizability. Which exhibit highest polarizability? Zinc, tellurium. Okay, zinc, tellurium will exhibit highest polarizability. Okay, now we can move forward to the question number 14. Okay, question number 14 is telling about for a dielectric with dielectric polarizability alpha, n is the number of dipoles per unit volume, number of dipoles per unit volume. The polarization in an electric field E, so polarization is the dipole moments per unit volume. Okay, so mu divided by V. And here alpha value is given. Alpha is nothing but mu divided by E. Polarizability. So we have to find just polarization. Total number of dipoles total number of dipoles. So E and E into V, N is there, total number of dipoles. We can also express in this term. Now, just see that we saw that polarization in a system with N dipoles can be expressed in this relation, N into mu by, because this N contains volume part, N contains volume by V. So polarization will be N mu. Okay, mu is Q into delta, and chi is epsilon minus R. That is this. Okay, so polarizability, ionic polarizability will be the mu by E, that is Pi by Ni local. So actually, as a result, E local has the local electric field enhanced by the atom. This gives the term ionic polarizability, and from this relation we can find that N alpha E local. Okay, so N alpha E local will give the okay. This is the value of N alpha E local would be the answer. Okay, N alpha E local would be the answer of polarizability, dielectric polarization value. Okay, it's the polarization value. Okay, now we can go to the question number 15. That the refractive index is 2. Dielectric constant of a material at a frequency higher than 10 to the power 16 Hertz. This is very important question. Up to 10 to the power 16, we have seen the graphical plot between epsilon R and E, means frequency. Okay, we have seen that first. Okay, so there is interfacial polarization. Okay, this is the equilibrium part, and this is the resonance part. This is the relaxation part. I have already shown this. Okay, so and here in this region, this is ionic, this is here. Up to 10 to the power 15 Hertz, up to 10 to the power 15 Hertz, it is showing electrical polarization. And after that, it is going to the value epsilon R equal to 1 value. This line indicates epsilon 1 equal to up to 10 to the power 16. 10 to the power 16. Okay. And after greater than 16, what will gives it? It gives only the value 1. Do not gives the electronic contribution. So greater than mu greater than 10 to the power 16 means it do not give electronic polarization. It do not give electronic polarization. Okay, it just behave as a linear dielectric. Means all the dipoles are ends. So linear dielectric. Okay, it just behaves as a linear dielectric. So in this region, only this option will be correct. Okay, now just we are just for a non-magnetic material, Maxwell's electromagnetic theory predicts that the dielectric constant update for electronic continuity will get the index of reflection. But it is this relation, we cannot apply this relation here. It is only true up to the electronic contribution. But above 10 to the power 16 Hertz, we cannot we cannot apply the electronic contribution. Then only the linear dielectric properties will be valid there. So the dielectric constant are mainly dependent in those part, ionic, electronic, and this. Okay, you are already aware of this. Okay, you can see here that how n square is dependent with epsilon r, that they are similarly Similar in carbon and germanium, that all gives electronic part. When n square gives this value, this means epsilon r, there must be inclusion of ionic or dipolar along with electronic charge. Okay, but uh, frequency dependence of dielectric polarization test. If the frequency of the field is very high, 10 to the power 7, no dipole system will be able to follow the field oscillation. And in such a situation, no mechanism will contribute when epsilon r equal to 1. But in these cases, okay, in these cases, 10 to the power 12, here ionic polarization will be available. Okay. So electronic ionic polarization charge dipoles can be considered behaving as a mechanical oscillator. Okay. And in the case of orientational polarization, means ionic polarization, sorry, dipolar polarization. There is no direct mechanical restoring force. The restoring force is only for ionic polarization. In dipolar polarization, not mechanical restoring. Instead, we have many statistical events that respond in various average results to the driving forces of electric field. So, a average net dipole's moment will be there. Is that clear? Okay. So, but in these cases, relaxation time appears, which I have told you. Relaxation time. In next class, we will learn about how relaxation time appears and how it responds in dipolar cases and even um, dipolar and interfacial polarization cases. There you will see the relaxation process. Okay. Where the driving force were to disappear suddenly. Driving force disappears suddenly. The ensemble of the dipoles will assume a net equilibrium state and random distribution of dipole within the some characteristic time called relaxation time. So driving force here suddenly decreased in these cases, and there is a span of time in which this span of time is called the relaxation time, in which dipoles will assume as a new equilibrium state where random distribution of the dipoles are found out. Resonance phenomena, and in this phenomena, in dipolar phenomena, no resonance phenomena will be appear. They are only relaxation phenomena will be appear. It is characterized by relaxation time instead of resonance frequency. So, what will be the answer? Answer will be 1. Okay. The electric constant will be 1. So, you already have learned much about this topic in this week, and I have done every question with sufficient answer and its explanation. And just checking, have I done every questions or not? Question number 4, okay, 5 has also been done, 6 has also been done, 7 has also been done, 8 it is discussed, okay. Question number 9 it is discussed. Question number 10, okay. 11, okay. 12, 13 I have done, okay. 13 I have done, 14, okay, it has also, okay. So I think every question, uh, I have discussed every questions, so we can now, it is already 7:56, so that time is, I have tried to finish within time. If you have any question, you can ask. If you have any question, you can ask. Okay, so no questions, so we can end the meeting. Okay, so good night and see you next session. Okay, see you in next session. Okay, right, we can leave the meeting.